Alright, so this is an introduction to partial derivatives. So what exactly is a partial derivative? Well, a partial derivative is when we take the derivative of a multivariable function, but only with respect to one of the variables present. So that means that the types of equations which we'll be taking the partial derivative of have two or more variables in it. The non-changing variables in the function are then considered as constants. So I'm going to show you just what this looks like real quick. Our notation looks like this. It looks like dx. And what this actually means is that we are taking the partial derivative, but with respect to x. That's what this variable representation right there means. Now we could also have it written as some other variable, so you could have something like dy, and that would mean with respect to y. This position, however, is what actually dictates the changing variable in the partial derivative. This fancy d's are what dictate that we're taking the partial derivative in the first place. So then suppose we have an example such as x plus y. Alright, in this equation, suppose we were taking the partial derivative with respect to x. Because of this variable position, x would be our variable and y would be our constant. So that means that y is comparable to any number such like 8, 6, 7, anything really. Alright, now I think the best way to teach you guys how to do partial derivatives is to just do some examples and walk you through the different steps of each part. So, as we can see from our notation up here, we are taking the partial derivative and with respect to x. So that means that all of our x's in our equation are represented as variables, as such they are. And then all of our y's in our equation would then represent constants as the non-changing variable. Then what I like to do is I like to move all of our constants to the front of their specific terms, because traditionally in terms which have constants, the constants are represented as the coefficients. So therefore it just makes it easier to visualize when you're taking the derivative how every step is actually taking place in it. We're going to rewrite this down here as dx, so the partial derivative with respect to x, of 6x squared plus 17yx plus y. And then from this new equation, we can definitely see that our constant coefficients are located here, here, and here. And then once you've done that, you can go ahead and take your derivative. So then, since the first term has no y in it, it's just the traditional derivative, so it's just 12x. And then since the second one has a coefficient out in front, what we can do is we can take the traditional derivative knowing that 17y is the coefficient. So the coefficient stays out in front, and then we multiply by the derivative of x, which is just 1. Then we add our next term, which the derivative of y, since y is a constant, is 0, since the derivative of any constant is actually 0 anyway. So then our final answer, when simplified, would be 12x plus 17y. Okay, so now we're going to make things even more complicated. Instead of taking our derivative this time with respect to x, we are taking our derivative with respect to y, as you can see from our notation. So that means that our variables are located here, and then the rest of our terms are considered as constants, right? Okay, so then it's also a more complicated function as well, because instead of just being a polynomial function, we also have trigonometric functions in our function. So this time we have to be careful when we take our derivative, and we can definitely see how that applies as we complete our example. Now, since our constants are technically out in front in all of our terms, we can just go ahead and start to take the derivative. So if we write this and take our derivative, we bring our constant out in front, and then we multiply by the derivative of our variable portion, which is 3y squared. And then we add the derivative of sine x. Now, since x is considered to be our constant, we know that the sign of any constant is just going to be a constant term anyway. Then the derivative of any constant is 0, so we can say plus 0 minus, keep our coefficient out in front, and then we multiply by the derivative of our next term, which is cosine y squared. And we all know by the chain rule that we change that to negative sine of y squared. And then we multiply that by the derivative of what's inside our trigonometric function, which is 2y. So then when cleaned up, our answer altogether will be 3x squared y squared minus or actually plus because our signs change, 6y sine y squared. And that is our answer. As you can see, our functions of sine and cosine act in the same way as they would in a traditional derivative equation. We just have to pay more attention to whether or not the variable inside the function is the one that's changing for the partial derivative. And with our final example, I'm not really going to fully simplify it because it takes a lot of work and it's easier to see it and how the steps come together when it's not simplified. I'm just going to go ahead and do the quotient rule for this problem. From our notation, we can definitely see that this is the derivative with respect to x. And what happens with the quotient rule is that you do take the derivative the same way. You just have to pay attention to how you're taking the derivative of either your top or your bottom piece, and whether or not you're taking the partial derivative with respect to the correct variable. So let's just begin by starting off and rewriting this as our actual thing. So we know the quotient rule. It's the bottom, so x plus y, times the derivative of the top with respect to x. So then you take the derivative, since y squared is considered to be a constant in this situation, so it stays out in front. And then we take the derivative of our x piece, which is 3x squared. And then it's minus the top piece, which is x cubed y squared, times the derivative of the bottom piece, which the derivative of x is just 1, plus, since y is considered a constant, it's plus 0. And then it's all over bottom squared, which is x plus y squared. So as you can see, it does work in the same way. You just have to be careful here of the changing variable. And the same goes for the product rule and the chain rule as well, as you can see from past examples. And that's the partial derivative. So I hope this has been helpful to you and that you've learned a lot.